name is Mike Harris, and I'm here to talk a little bit about, some 5.0 to 5.5 work on NUMA, VCPU scaling, considerations for GPFS. So we'll talk about VCPU scaling first, and it's a little bit of a change, and some people might not be familiar with the term exactly, but I think people have had some exposure to it even on your laptops. We set limits that we both warn and enforce based on virtual CPUs, or we'll call them VCPUs, not on physical sockets or on what you would call a classical core, on a socket, or multiple cores on a socket. So let's talk about that. A VCPU, it's basically a hardware slice or a subdivision of a physical CPU, and it's comprised of all or part of a physical CPU. It's based on configured hardware core threading levels. A lot of you have probably heard of hyperthreading on Intel, for example, and x86. It's their term for some parallelism and threading within a core, and SMT on power systems. And as a quick refresh, they basically figured out that there's a lot of capability in the cores, and if it was totally single-threaded, there's a lot of circuits that possibly could have been doing something in parallel or speculatively that just wasn't happening. And so now they actually allow, well, not now, but have for a while allowed logically splitting up a physical core into virtual cores. And depending on the chip and the application, sometimes this can work out really well. It's probably not uncommon for test stations and things to run with at least a hyperthreading of 2, sometimes 4. So the key thing there is it's actually the scheduled processor entity by Linux and AIX, okay? And so you can schedule against it. Generally, it runs well if you don't set the level too high. The key thing is, if it's a scheduled entity by Linux and AIX, then it's really what we need to worry about in GPFS. We have structures that are based on the number of processors, and there's other things going on. And so GPFS really, spectrum scale really cares about basically the number of schedulable processor entities. So VCPU, it's a hardware slice that you can generally configure. You can do it dynamically on power. Hyperthreading on x86 usually requires a setting at boot time. So one of the things we've done is, I'll talk about some of the prior limits, but we've tested and established some warning and also some hard CPU limits. We've seen some pretty interesting machines come through that had extremely high, CPU counts, and so instead of just having things in the FAQ, we worked with some of the customers, as we always do, on both testing, and then we also have limits in place that are checked when GPFS starts up. These, in general, are also based on what you might consider classic SMP or symmetric multiprocessing and NUMA hardware configurations. And I'm going to talk about NUMA in a few minutes as well, but there's some more interesting configurations out there that work in certain environments that are a bit more challenging for something like GPFS that kind of wants the whole machine, especially on the server side. So our testings and warning limits basically presume that we're on a classic, relatively classic configuration that has a low NUMA complexity, and I'm going to get to that term in an upcoming slide. Low internode latency, because NUMA has to do with non-uniform memory, and so you want that to be fast. And high bandwidth, right? You want a high bandwidth between the NUMA nodes. So classic SMP machines generally qualify, and if you're within our limits, then we basically expect things are automatically going to run really well. Large LPAR and virtualization hosts like the E980, MH9119, things like that generally work well, and we've done some qualification on those. There's also large, configurable machines like, for example, the UV2000 and things like that, that have a very high NUMA complexity and high latencies due to how it's basically stitched together a lot of CPUs and boards and chassis, backplanes, and even interconnects between chassis. So as you get into more complex machines, there may be there may be some issues, and it really just kind of depends. So we're going to talk about that a little bit more. All right. Okay. So on CPU scaling, the FAQ, what's the current maximum tested limit for SMP scaling at this point? Okay. The largest to date is 192 cores. And that was providing a vCPU count of 1,536 vCPUs. And that was, that particular one was on a power 8 or 9, 192 cores at SMT8. And that was in concert. We did it internally and then also in concert with a customer. The largest, so basically 1,536 on 192 cores. The largest NUMA complexity metric, and I'm going to get to that in a little bit, is 3. So these are the limits that we're measuring when when spectrum scale starts up, and we may warn or prevent GPFS from starting, based on those. So at code, like I just mentioned, supported, which we consider we totally expect it to work just absolutely fabulously, is less than or equal 256 virtual CPUs. And, our current Power 9s match that. Most machines that aren't big LPAR type machines support that. Above 256 and up to 1,536, we'll issue a warning. GPFS will start up, but it will issue a warning that says the vCPU count is higher than our recommended, and that there may be issues, and that we prefer that you talk to engineering to discuss. As I've said, we've run on some large machines fine, but there's some large ones that we've had issues with. So above 256, we'll issue a warning, but GPFS will start up. It doesn't generate a help, goes into the log, and it's available in the supportability dumps and things like that. That 1536 is a hard limit. So if we see greater than 1,536 virtual CPUs on the system, then spectrum scale will not complete initialization. It'll basically say there's a hard limit, you exceeded it, and we're not going to start up. And it will shut down after logging that information. The virtual CPUs are as reported by the operating system, and C groups, for example, cannot be used to bypass VCPU limits. And I'll talk about that a little bit more in an upcoming slide. So let's talk about the NUMA considerations a little bit more. A lot of people have heard of the term, some haven't, and they may not really understand it. So I'm going to talk just at a high level about it. NUMA refers to non-uniform memory access between memory and processors, and to some extent, sometimes I/O adapters and things like that. But in general, between memory and processors. So, you know, your old classic single core with the memory right there is a uniform memory access. If you start getting two sockets and then sets of memory in the middle, then you're introducing a little bit of non-uniformity, kind of depends. But it's also done because if you get high counts, it can be difficult to have everything have totally even latency. So if we look at this diagram down here, the key things are there's two groupings of processor, bus and memory. So there's two groupings of that. And as you see, the four processors on each of the buses, they're close to each other, right? They have access to the same block of memory just through that little bit of a distance. That memory is their direct memory. In this type of a system, all processors can see all memory and access all memory, but since we've grouped it like this, if it needs to processor on the far left needs to access memory that's in the right module, it has to take an extra take an extra step through a bridge or a memory interface and to satisfy that memory read or write. And it's all transparent, but that does take a little bit more time, and it's also, so that's going to add a little latency to that. And also that connection between those memory, that's going to have, that's going to use bandwidth. So if the bandwidth isn't equal to the bandwidth on both of those, and the communications between is heavy, then there might be contention, and that can also slow things down. And we're going to talk about a metric on that. So the basic concept, it's non-uniform memory access between memory and processors. It's generally not a problem on what you might consider kind of a classic symmetric multiprocessor machine. It can be more. So in this diagram, to summarize again, the interprocessor memory access, it's faster within their own group or NUMA node, sometimes also called a NUMA domain, than to the others. It's transparent, and then this internode latency impacts multi-threaded programs that expect SMP uniformity. So things that aren't actively coded to stay on one domain or another can be impacted by this. So how is NUMA characterized? Okay, the general characterizations are the number of NUMA nodes or domains. And so in the prior slide, that was basically those two groups of processor and memory, and then there's an interconnect. We recently, to try and quantify this and put it in specifications and limits, we coined the term NUMA Complexity as a metrics to characterize as value. And so the NUMA Complexity looks at NUMA nodes and the distances and characterizes what we perceive as a NUMA complexity to see if a machine might be a possible problem or not. Okay, so the number of NUMA nodes, the latency between the nodes, okay, and what we look at is, in particular on Linux, there's a nice thing called NUMA control, and you may need to install that package. The core functions are there, but you may need to install that package on your machine. So there's a NUMA node distance is reported by Linux command NUMA control-hardware, and I will have an example of that coming up in an upcoming slide. One thing to notice is, we're running on hardware and we see things from the operating system and the libraries, and it gets it from the firmware. And so the values that you see and understand and are actionable are based on, they're reported by the firmware, and they're dependent on the firmware. And the firmware may or may not give you all those values, and it may not be always usably accurate. I'll talk about that a little bit more, but the firmware basically says, hey, there's 2, 3, 4, whatever NUMA nodes, and here are the processors that are on each NUMA node. Here's how much memory is on each NUMA node. So those are attributes. IO adapter would have some similar information, but it is dependent on what's reported. For example, a couple of years ago, I was just looking at, there were two essentially equivalent, not server, in this case it wasn't a server motherboard, but things my son was looking at for gaming. There was an AMD and a Intel, and they were truly identical, or essentially identical architecture-wise, from a deep technical perspective, but they each reported NUMA values a little bit differently. So these values are a good start, but it's a little harder on the NUMA stuff to set hard limits just based on what the firmware did or didn't report. So one of the terms I talked about is NUMA complexity, right? And so that's pretty important, right? Is if the complexity is high, we're probably not going to run very well. As I mentioned, it's a spectrum scale coin metric that generally characterizes the complexity of the NUMA environment. And the core definition is the next bullet. It is defined as the number of distinctly different NUMA node distances. We talked about the number of nodes and the latency, which is represented by NUMA node distances as reported by this command. And I'm going to show that example at the bottom of this page. I'll just mention the warning limit is 3, and it corresponds to machines that we're known to work well with. And also, as I say, this particularly is a characterization metric. We've seen some machines with a higher value that run well, others with similar higher values that don't work well. So for the complexity metric, we measure it, we report it, but we won't refuse to start up based on that. As with all these other values, they're logged at startup, and they're also, if you do a MMFS ADM dump NUMA, then you'll get all these values at that point as well. So customers and support can look at what we saw and think about things. So let's look at an example. The following system This is one of the Coral systems, actually, one of the Coral Power 9s in our research scaling cluster. It has a NUMA complexity metric of 3, as we're going to see from this, but I'm going to note that I know that one of those nodes, sets of nodes, are graphics adapters. And so before I get to that little picture, we actually look at the complexity of nodes, things that just have CPUs and memory and everything else. So we'll report both. So in this case, we would report 2 for without adapters and 3 with. So if we look at this, this is at the bottom of NUMA control hardware. So we see nodes 0, 8, 252, 253, 254, 255. That illustrates something I didn't put in detail here, but machines generally don't list NUMA nodes sequentially. So there's not a node 1 that's hidden or disabled for some reason. They just chose to have one 0, have one 8. It's probably how they do things in hardware. A different machine might show NUMA nodes 0 and 1. So just know that you can't, that space of the node numbers may be sparse. So we have 0, 8, 252, 253, 254, 255. So in this array, right, what you'll see is, right, between 0 and 0, it's not formatted great, the node distance is 10, 0 to 8 is 40, and 0 to one of those 250s is 80. And that's intended to give a metric of the latency or cost of going between any 2 NUMA nodes. So we see that 0 to 0 is the fastest, and 0 to 8, for example, it's 40, which is 4 times 10. The intent is that those are actually proportional, so that going from 0 to 8 is 4 times worse or 4 times higher latency. In practice, that's not the case. The spec says it starts at 10 and it should be integral multiples of 10 and represent the cost of going between nodes. In this case, they have 10, 40. I know it's faster than that, but it gives an illustration of that. You just can't know that it's 4 times the expense. But if we look at this, we see we have NUMA node distances 10, 40, and then 80. So that's how we count a NUMA complexity metric of 3, because there's distinct node distances of 10, 40, and 80. So that is a NUMA complexity metric of 3. Since we can't look at latency, we don't. In this particular hardware, I know that the 250s are NVIDIA graphic adapters, and for GPFS doesn't care about that. And so, as I noted, GPFS or Spectrum Scale will log that the NUMA complexity is 2, which we like, for basically nodes that have CPUs, and it's 3 including all nodes. So I hope that gives you a little understanding of what we call NUMA complexity and how we see the overall architecture is something that's likely to work well outside of high CPU counts. I think I've talked a little bit about this, but NUMA node distance, it's a platform metric. to characterize the latency between any nodes. It's intended to be integral multiples of 10. I've always seen it start at 10. It's supposed to start at 10. I've seen 22s and things like that. It's intended to be an accurate conveyance of internode latency. Again, that varies. If you really want to know, you've got to write some code and measure it. As I've noted, it's reported by platform firmware if it's reported by the firmware. If firmware doesn't implement it or code that table, then you're not going to get those values. And so as often as not, it's somewhat ad hoc, but it still gives an idea of how complex the NUMA is. If it's 5, then we're going to be concerned and really want to look at a machine. If it's 2, that's generally pretty classic, and it's probably going to work well. Spectrum scale, we report the values and views of NUMA complexity and NUMA distances. We don't make performance decisions based on this because it's not guaranteed to be exact and consistent enough for us to do that. But it is advisory in logs and dumps. When there's performance issues to be identified, it can be useful if we see odd performance and we see that the NUMA complexity is high because it's a machine that hasn't been discussed or evaluated, then that can clue us in that might be part of a problem. And it helps us understand machines we haven't seen before, like the UV2000. A lot of this code wasn't in place yet, and so we had to ask for a lot of this information. And now we just have it on the dumps. NUMA considerations. So NUMA awareness is a good thing if you're aware of the NUMA configuration of your machine. You can know if there might be issues, but if you can take advantage or at least have spectrum scale, for example, do things a little differently based on knowledge of the NUMA, then you can run better on a machine than just presuming. So spectrum scale, we're working on increasing the awareness, enhancing it. Spectrum scale right now, for example, for some of the advanced customers familiar with NUMA control and running programs under NUMA control, and perhaps at some points even starting GPFS with it. Spectrum scale can be configured with spectrum scale configuration parameters to start up with most Linux NUMA control options. Memory interleaving control is a common one. There are some other ones. So you can set up the cluster to automatically start with desired options rather than having to do that yourself. Verb's RDMA, it's NUMA aware. You can see that in some of the dumps. It's not yet proactive in that space, but experiments show that could be of benefit. As noted, InfiniBand RDMA adapters may benefit from thread and memory locality. And a point on that is on, for example, in the lab, some of the machines I have that have InfiniBand adapters, where is that on the memory bus, right? On a lot of machines, it's sitting off, it's basically sitting in the middle with the memory. And so both NUMA nodes, both sockets have equal access from a NUMA perspective to the RDMA adapters. Okay, and so it's not really an issue on a system like that. But if we look at a more complex hardware, we'll find often that the adapters will be in, like say you have 4 InfiniBand adapters, the 2 of them, there may be each 2 on a NUMA node. And so, for example, if you're accessing, adapter 4 from the other NUMA node, it's going to be a bit slower, and if it has to pull that memory over, it's going to be a little bit slower. So this type of awareness can benefit RDMA, and as I note, though, it kind of depends on the machine. If there's separation of where the NUMA, the InfiniBand adapters are across the NUMA space, then it's likely to be a benefit. If the adapters are sitting in the middle, then it may not buy you anything. But this is an example of where awareness can help out on certain machines. We've also done experiments to improve the NUMA efficiency of page pool allocations, and we're evaluating that. We expect the benefits of any such improvements will depend on the hardware configurations being evaluated. And that really goes hand in hand, for example, with the InfiniBand and RDMA adapters, because they're moving that memory, and so if you've got low complexity and everything else, then you might not see improvements as much as on bigger, more complex machines. So what's possible? It depends on where memory and hardware reside, and also the adapters. Not really an addition, but it fits in with this. I wanted to talk a little bit about C-group awareness. And for those that haven't been exposed, the C-group or control group is a grouping of processors in memory that a processor thread is assigned to. This is more of a Linux type thing in general, but a C group can be created and changed dynamically or pre-configured. It's generally used to limit resources. And, for example, Coral has played around with isolating a lot of system processes to a few cores to reduce jitter on the application. So that might be one use of a control group. We don't, well, I'll get to that. We don't use them much, but people have tried to use them with GPFS also to work around certain limits. So Spectrum Scale has a basic C group awareness for what would now be known as C groups V1. Red Hat 8 has a C groups V2, which is better in a lot of ways, but it's kind of a orthogonal organization, and so it requires a little more work. So we are C group aware, but it's largely informational logging and dumping of the system versus an actual run environment. And I'll get to the reasons for that. C groups V2, it's in Red Hat 8. It's not the Red Hat default. So if you load up Red Hat 8, everything should be fine. V2 is not qualified yet. Shouldn't be any big issues, but some of the NUMA stuff, maybe it wasn't important. So it's not formally supported using C groups, that is. Spectrum Scale, for example, it's not notified of C group or CPU set changes, so it can't log or react to any changes. So the administrator can go in and make whatever changes he wants to a C group, stuffing it in a smaller set of CPUs, a larger set of CPUs, any of that. It can change the memory available, usually only increasing it, but it can change the memory available. So you can change and mess with a lot of things, but GPFS doesn't know that. And so we can't even count on what we start up with being what we're going to be running with later if someone changes the C groups, for example. So partly for that reason, and also because GPFS can possibly end up with the entire machine or its resources of entire machine, we use a system limits for limits checking. C groups, CPU sets, they're dynamic, so we must be ready to handle the entire maximum possible system configuration of CPUs, memory, and hardware. So if you try to use C groups to set CPUs at 1024 instead of 2048, we're still not going to start up because, 10 seconds later you could change that to give GPFS all 2048 CPUs. We wouldn't know that, and we might start running poorly. So C groups and CPU sets can't be used to bypass any of the VCPU or memory limits checking. So as a summary, Spectrum Scale version 5, it brought VCPU, NUMA, and C group awareness and an enhanced roadmap for those. Classic S&P multi-socket motherboards with sane NUMA characteristics remain the gold standard for Spectrum Scale. A sane NUMA configuration has a NUMA complexity of 3 or less with low latency and high bandwidth between NUMA nodes. Most machines we all work with are fine. Intelligent use of virtual machines and logically partitionable machines to high counts can work on sane architectures. And like I said, we've done some work on E980 and MH9119 and other machines, and we've seen issues on things like UV2000s. So the amount of CPU and memory that are required for the reasons you want to use Spectrum Scale require sane NUMA to work well. 2,000 threads running on a poor NUMA configuration is going to be challenged. VCPU scaling, NUMA, and C group awareness and enhancements are ongoing. Spectrum Scale is run on an extremely wide variety of different hardware configurations, and we work closely with our customers to stay at the best at what we do. We're really glad to work on issues that might be seen in new cutting-edge configurations, and if you've got something, contact us, and we'd be glad to work through making sure it would be a good machine, and if there are things we can do. That's it. I've got some links here, just some high-level basics, and I can take any questions.
Yeah, Mike, I think there are 2 questions in the Q&A chat. The first one is the MMFS log is now showing the following message. What does it mean? Warning, NUMA BIOS platform support for NUMA is disabled or not available. NUMA results are approximated, and GPFS NUMA Awareness may suffer. So what does it mean?
So what machine was this on?
HP DL380 Intel system.
So there's, was it running Red Hat or what was it running?
I don't know. Red Hat?
Yeah, so it's like I mentioned, what we get, which comes from, live NUMA, comes from both the operating system and the firmware. And so it's basically saying that one or more values that we're looking for aren't available. The first thing to do to check is do an install of the NUMA control package. Generally on Red Hat, the core libraries are already there. You just might not have the NUMA control command. But it basically says some of the values that we want we're not getting from the firmware when we make the library calls. Mm-hmm. And so, yeah, it's so that's the first thing is try and install the package. But one thing I want to note here is that sometimes, like on one of my lab machines, for the InfiniBand adapter, it says its NUMA node is -1, which basically says the value is not specified, but everything else is available. So sometimes we'll find that certain specific values might not be available. And some of the data is also aggregated, like when you do a NUMA control hardware, some of that just comes from the processor and /proc and things like that. So it's usually not binary that we get nothing. And I'm not otherwise familiar with the DL380. But you know, I'm interested in seeing some other command output on it to get a little information on it.
That's how I know the customer and can connect you. But what do you recommend in general if a customer is seeing such a message? Is it appropriate to open a PMR or?
No, it's not, because this is not GPFS having a problem, and this is just GPFS saying, I'm trying to understand this machine, and the machine's not giving some of the information I want. And so, for example, we always know the number of CPUs, and so we're going to enforce that limit. The NUMA complexity and things like that, sometimes we can't get that, and that's an advisory value anyway. And so for that, you know, we'll note that we couldn't get some values, and then we'll just continue on. And it doesn't even mean it's not going to run well. It's just that we couldn't find that, and you know, we can't report it later is all. So there's no, I mean, a PMR wouldn't do anything. It's a hardware thing with the vendor, and it doesn't mean that there's going to be a problem.
Okay, so meanwhile, further comments here in the chat. So it's on the 5.1 beta, NUMA control is already installed, and now InfiniBand adapter in the system. So
probably a NUMA control -- hardware is probably going to show, you know, one or more expected values is either not available or not even have a line for that. You know, I'd have to look at the logs for that. But, you know, for example, I was doing some early work recently on a new Z system, and I got the same thing, and they called me up and said, what's going on? And we discussed it. And then, you know, one of the hardware guys is like, oh, yeah, I need to turn that on in the firmware, right? So,
okay.
That was all that. That was all that. That was. They intended to, and on this new firmware, they just hadn't done that yet. So it doesn't mean you're going to have problems. It just means that you know, I couldn't get a value to report that might be useful in a support situation, or like an InfiniBand adapter that doesn't tell me what node it's on. I can't make a decision to think about assigning it to a particular NUMA node. I've got to just leave it available to the entire system, right?
Yeah. Okay, then there is another question. Are there any special NUMA configurations for AMD systems necessary compared to Intel systems?
You know, generally the AMD and the Intels, at least at a chip or kind of a classic motherboard level are fairly comparable. They might report a little different. The EPIC is the AMD EPIC system. At least the first generation, is that Rome or Naples, is a bit more challenging. The first one has some fairly complex NUMA with some high latencies. That one might not, run very well. And one of the things I want to note too is sometimes it depends on how this hardware is glued or configured together, right? Like, a UV2000, right? It's got, I think, a socket or two on a board that's in a module, and then there's multiple modules in a chassis. There might even be a level before that. And at each of those groupings, there's a memory bus interface, and it gets all the way out to the chassis, which then gets into a memory bus that links all these chassis in a rack, and it can even be extended, for example, to another rack. And it's all a common memory space, but when you start going from, one processor on a module on one rack to another, you don't see that, but the impact is great. And so that's an example of common chips that are relatively sane being pieced together in configurations that might become challenging from a NUMA perspective. That fits also with like an E980, right? Its configurator tries to allocate adapters, processors, and memories that are all close to each other, but sometimes it can't, or if there's manual intervention, sometimes it can't. So a good configurator for something like that tries to allocate well, but that also doesn't always happen. And that's also another example of a machine. Like most virtualizations show you extremely sane NUMA configurations, right? They're not going to expose or don't try and expose that these processors are on, 4 different blocks and things like that. They usually just say you've got a lot of times one NUMA node with all the processors, and that's not the case. So that's a different example of a configuration that doesn't report well, and why we want to look at and talk about machines like that.
So just a quick add-on to the answer that Mike gave. We have been having we have a very good relationship, obviously, with our and System Z, and we get to work on these kinds of things with them. We also have a pretty decent relationship with Intel, and we get access to early hardware so that we can start getting ready for the next generation platforms and new capabilities that they're adding. And very recently, we have started working with vendors like HP and directly with AMD to take into account the stuff that they're doing with their chips and the NUMA intricacies that brings. So we have a lab where we get access to all of this kind of hardware and we try things out. And so we have adding AMD-based servers with the latest generation, because one of the things very interesting about those AMD chips is that they have pins that are limited, but you can configure them in many different ways, right? You can have a lot of I/O coming out of a particular processor, or you can actually have really, really strong SMP bandwidth between 2 sockets on the same board, or you can get a sort of a hybrid kind of a setup. So we are trying to take a look at AMD specifically for addressing some of these NUMA concerns with their chips. The other thing is, if you were paying attention to Hot Chips, the conference, IBM did a very, very detailed unveiling of the Power 10 chip there. And in Power 10, there's going to be a mode, right, that make it possible to tier E980 kind of configs to additional, like a new level, and you'll be able to build a very what Mike was referring to as the complexity, the NUMA complexity will go up to 4, and we're already starting discussions with that team on how to handle that. So this is always an evolving situation. If you have systems or if you have some things that you would like to take a look at us, let your local rep know, open up an RFE, or contact us through the mailing list, and we'll be happy to engage.
Yeah, I agree with what PC said. I have a comment on the last couple of questions too. I mean, in regard to Renar's question about that error specifically, I mean, I just looked at the code, but it means we failed to load the NUMA library. It doesn't mean it's a BIOS problem, but from just that error, we can't tell exactly what's wrong, right? You've got the necessary RPM. We would do some more digging, right? And PC's exactly right. The right way to pursue that is either a Salesforce case or the forum, but that's what that error means. And on the comment about, optimizing NUMA in general, I mean, there was a comment as well about, what is the right settings for P9. I'm going to say there's nothing you should need to do currently in scale in terms of, I mean, you obviously make choices like hyper-threading or SMT, right? Those choices are applicable to a given workload. And I can tell you, we just looked at some cases where, depending upon whether we enable or disable hyper-threading, we may see different results for, let's say, a write workload versus a read workload. This is common, right? These kinds of, we'll see different behavior depending on the workload. It's not a simple scale question. It's often a question of how do you tune, your resources for the workload you're running. Two separate points there.
Okay, so I understand it in a way that it depends on the workload. So maybe some setting is good for spectrum scale, but bad for the application, or the other way around. So you have to try it out and figure out what is the best for your overall system performance.
And I think there's going to be a new sort of way to also look at these. For example, people are running very, very complex NUMA domains now, and they can get affinity by running their workload in a container, and you can use Kubernetes, OpenShift, or whatever you want, right? You can even have a Singularity container to sort of restrict that NUMA domain to get that affinity. But if spectrum scale is running across the system, some of the tricks are not available to us. By the way, we are actually looking at, doing some more work. John's actually leading that effort to see how we can affinitize some of our threads and memory, et cetera, even more. So this is going to keep going for us. And meanwhile, if we don't, so stay tuned for a new version of Spectrum Scale or new capabilities where Spectrum Scale runs in a container, and we should be able to take advantage of some of that same NUMA-ness or ability to affinitize some of that stuff if possible, right? Because again, if you want to run it and make it available across the board and have lots of NUMA domains, right, it may not be possible for scale, but there are going to be new options that will become available there.
I think we have answered all the questions now in the chat. So, so it's time to wrap up. We are about 1 hour or 1.5 hours about Belgian time. Yeah. So I want to thank everybody here who stayed till the end. Simon already had to drop, so he asked me to close this. So the charts and the recording, and also the Q&A and so on, we will post it on the user group big page, spectrumscaleug.org. And I think that's it for today. Yeah. Thank you very much. Bye-bye.